summary. Okay, this is kind of a summary about monolithic sensor, and it's going to be a very detector overview on a little bit what is the technology and what are the experiments that are currently using this technology and what are the future prospects of these technologies, and also what are the experiments that are kind of considering to use those. Now, in more detail, first I start with why monolithic sensors are the future, or at least the very advanced present, and how they compare with more traditional silicon technologies. And then the king among the monolithic sensor is the Alpide, not because it's the best, as we will see, but because it's the most commonly used one, because it's used in the ITS, inner tracking system of the Alice detector and the LHC. And then we will see the evolution of the Alpide, that is called the MOS, because it's stitched monolithic pixel sensor. We will see that this allows a sensor to be bigger than what can be actually manufactured. And we will see how this is convenient and why this is actually where everybody is going with this monolithic technology. And then also we are going to see the alternatives. So not only other chips, but also other technologies that are always monolithic, but they design a sensor that has a different approach. So it's completely different, even if the application is going to be the same. So it's always monolithic and always for tracking detectors. And we will see, as anticipated, also what are the future application of those present and future technology for the monolithics. Okay, so let's start with the motivation. Now, every not only LHC experiment, every particle detector has a tracker, and the inner tracker of CMS, Atlas, or the forward, the vertex locator of LHCb, or even the proton precision spectrometer of CMS, they are equipped with pixel detectors. What they have in common is that they are called hybrid chips. So basically, you have one piece of silicon that is the sensor, and it is done with a technology that is optimized for a sensor, so it's wide and big and high resistivity, and you can apply very nicely the bias on top and on the bottom. And when the particle is crossing this sensor, it's generating a lot of charge for the whole thickness of the sensor. And then we have another piece of silicon with another technology, another foundry, another production, another design, everything completely different, that has simply the same geometry, and pixel by pixel, they can be connected with a bump bonding, which can be a gold ball, or it can be a solder ball, like in the microscope picture that you see below. This is basically the sensor on top and the readout chip on the bottom, and they are connected with solder bumps. Now, this is the standard because, like I said, you can have one technology for the pixel, for the sensor, and the other technology from the front-end chip. And this is very nicely because you are decoupling and you are doing one thing very well and the other thing very well. However, this is not so nice, because what happens is that I mean, there are a lot of advantages for this. For example, it's very radiation hard because, like I said, you can have a sensor in this manufactured with the technology of very radiation hard sensors, and the electronics designed with the techniques to make it radiation hard. And also you have a lot of flexibility because you can change the sensor without changing the readout chip, or changing the readout chip without changing the sensor. So if you have a newer technology for the sensor, or if you have a different application, for example, you want even more radiation hardness, you can use a 3D architecture for the sensor. Or if you want to have like a readout chip that has less power consumption, for a lower power consumption, you can change only the front-end chip without changing the sensor. Now, another very nice thing is that you can put a lot of logic in the pixel, because of course every pixel is needs a dedicated logic, and what you do with this logic is defining the capabilities of the whole detector. For example, if it's a tracker detector, you just need to know if a particle hit the sensor in that pixel or not. But what you can do is that you can add other electronics. For example, this is the ET-ROC, the readout chip designed for the CMS MIP timing detector. And you can see that inside, not only you have the amplifier and the discriminator, but you also have a TDC, which is time to digital converter, which is basically measuring the time of arrival very precisely, and also the time over threshold, which can give you either a correction for the time of arrival, so you can have a timing detector, or you can measure the energy, so you measure the full time duration of the pulse that is actually proportional to the energy deposited by the particle. And this might be nice if you are doing spectroscopy or if you are doing a calorimeter. So all those things are very nice, and of course this is just the tip of the iceberg, because this is just an introduction, but there are a lot of problems. First of all, the high power consumption, because you have one sensor that is the full thickness of the silicon, and then you have in this case, for example, you have a lot of electronics to power, and this particular case, it's optimized for low power consumption, but still it's relatively high, as you will see with respect to the monolithic. And then there is a very complicated mechanics, because as you see here, you have the sensor that is literally bonding on top of another thing, and then you have the readout chip that is connected on the with wire bonding to a flex PCB that is on top of the sensor. And this, if you squeeze it too much, if you warm it up and you cool it down, you have thermal stress and mechanical stress. This is very complicated thing. And also you need one foundry to produce the sensor, one foundry to produce the readout chip, one company that is doing the bonding, one company that is doing the wire bonding. So this gets expensive very quickly. And also, if you consider that, I mean, you have to do a few square meters of sensor, it doesn't really matter. If it's even twice the price, it's worth with respect to the R&D cost. But if you have to design detectors that have tens or even hundreds of square meters of sensors, then the cost per sensor becomes a problem. Now, we are usually thinking that we are state of the art in this kind of R&D, and we are, because for radiation harm detector, of course, high energy physics, nuclear physics research is at the state of the art. However, if we think about silicon technology, there are many companies that are way ahead of us. And in this particular case, we also have example of hybrid approach or monolithic approach. And those are two microprocessor, very high level, both of them, and they are both very recent. And the one on the left, you can see that there are chiplets. So there is two GPUs and one GPU, and they are separated. And so this is hybrid because they are connected on the same microprocessor, but they are different pieces of silicon. While on the right side, you see the Apple M3, the one that you probably have in your laptop, where everything is included in the same piece of silicon. Now, the same pros and cons that I was discussing before are also applying here. The AMD Ryzen 7000 is for power, brute force, so it's a lot more powerful than the M3, but the M3 is optimized for laptops, and so it's a lot more power efficient, and the battery life of the laptop is a lot longer. Also, this is more expensive for the R&D because everything is in one. The yield is probably much lower because if something goes wrong in any of those components, you have to throw away the whole chip. But in the end, the cost per chip is going to be lower because you produce one wafer and that's it. That's all you have basically the whole laptop there. Okay, so after this introduction on the motivation why we need monolithic sensor, let's move on and let's see actual application. So we start with the Alice experiment at CERN, and we focus on the inner tracking system. And I'm sorry, the it's pointing somewhere else, but of course the inner tracking system is here. And what you see that we have an inner barrel and outer barrel, and overall we have that this is a quite considerable amount of silicon. In fact, we have 10 square meters, and also it is quite a high number of pixels. Indeed, it's 12.5 gigapixel, which is considerably more than CMS and Atlas. And this is also possible thanks to the fact that this is based on the Alpide, which is a monolithic chip. However, if we see a little bit more in the details, the inner part, which is this, it's smaller. And like always, when it's smaller, it means that you are closer to the interaction point. So it means that you need a higher resolution, but at the same time, you need a smaller surface. So you can have more pixel, you can have something that is kind of more expensive, but you have to be careful because you want to be careful with the material budget, and you want to also be careful with the resolution, because everything you put there is going to affect everything else in the tracker and in the full experiment. So in this particular case, we have 9 sensors that are monolithic, and we are going to see immediately the details. They are glued on a cold plate, and then this cold plate is water cooled, and then you have 3 layers with a total of so 12 plus 16 plus 20 staves. Now, the outer layer, like I was saying, is a little bit more relaxed for the resolution. And actually, in this case, we are using the same chips, so same resolution, but we are sacrificing the readout. And so we have a limitation in the bandwidth, the number of hits that we can transfer out. We are also a little bit more relaxed on the thickness of the sensors, because working with 50 micron sensor is tricky. And they are more fragile, they have to be thinned more, they have to be processed more. And also, we can afford to have layers that are overlapping, so we have more effective coverage, but at the same time, we have more material in the way. Now, let's go to like I said, to the king of the monolithic sensor, which is the Alpide. Now, the Alpide was specifically designed for the ITS upgrade, and this is why we call it ITS2. And it's using a process that is called tower jets. I will show you a little bit of details about this. But the chip is what you see here, and it's 3 by 1.5 centimeters, and it's you have square pixels, and you have basically 512 times 1024 pixel, and you can apply reverse bias. As we will see, the reverse bias is not needed, but it's useful if you have irradiated sensors. Now, the way it works is that you have in-pixel electronics that is, once again, on the same piece of silicon, because this is monolithic, and every pixel has its own amplifier, a comparator, and then a memory. And then all the pixels are controlled and read out by the electronics that is at the side. And you can see that there is some electronics on the side, some control electronics, because all the wire bonding is done here. This is an approach similar to hybrid pixel. It's just that in this case, this is one piece of silicon and everything is included. Now, one particular thing is that since this was designed for Alice, Alice is using something that is called continuous readout, and this is using a global shutter. So this means that all those pixels, they trigger at the same time, and whenever they have something like one hit or a cluster, they send it. They are not going to wait for a trigger, because the system, the trigger system of Alice is capable of running in continuous mode. So basically, instead of taking only the data when you have a trigger, it's taking the data continuously, and then there is a timestamp that allows every data to be synchronized. Now, this is the section of what we were calling tower jets, this is the tower jet technology, and you can see why it's called tower, because it is an epitaxial layer. Basically, to do this, you need several layers of different quality, different types of silicon. And in this particular technology, what they do is that they start with one particular type of silicon, and then they epitaxially grow the other type. And the other thing that you can notice here is how everything is together. And so you have some CMOS electronic, you have NMOS and PMOS, which together it's CMOS. And this is separated by those P well and N well, and by the region where actually there is the sensor part. Now, this is also another thing that is clear from this picture is how when the particle is passing through the sensor is creating pairs of electrons in the hole, of course, but those are not collected immediately because first they have to diffuse to the zone where there is an electric field applied, which is the white part here, and then thanks to the electric field that is applied, they can drift. So this is actually already showing us a disadvantage of this particular approach, because it's nice, because here you can have everything at once, but you need time to collect all those charges, and this makes the sensor relatively slow. Now, what is happening in every pixel is, with more detail, is that first of all, you have some pulsing that is embedded because you want to test, you want to do some calibration with the threshold and so on. Then you have the amplifier, which is the same for all of them. I mean, you have several copies, but they are configured in the same way. So you have some parameters, but they are global for the whole pipe. And then you have finally this part that is the digital part, and you can see the strobe. So basically, if you have you have a particle crossing, but you don't send a strobe, this it is not going to be latched, which means that it's not going to be stored in the in-pixel memory, and then it's not going to be read out. And this is needed because you want to be sure that all the pixels are sending time-consistent hits. And so if one pixel is hit before than the other, when there is a strobe, it's sending data. If there is no strobe, it's just forgetting about that data. And the other thing that you can see here is that the peaking time is 2 microseconds. Now, this is unfortunately a problem due to the fact that we have to start by diffusing the charges and then they can drift. And this is a limitation for the LHC. Because as everybody knows, we have 25 nanosecond branch crossing. So this pixel is not, using this sensor, it's not possible to actually associate one hit with one particular branch crossing. This is not a problem for Alice because, like I was saying just a few seconds ago, we are using continuous readout. But our time precision is going to be on the microsecond level. Also, the pixels are very small. They are 20 microns times 29 microns times 27 micron. And this allows to Alice to have very relatively low pileup. Now, the behavior with radiation is actually considered fairly good for the application. You can see here that this is the efficiency with respect to the threshold in electrons. Now, you don't really care about the threshold in how many electrons are in the threshold, but what you care is this red line, which is the fake hit rate. So basically, you need to have a threshold that is low enough to have a very high efficiency, but at the same time, high enough to have very low fake hit rate. And you can see here that the fake hit rate stays low with all the thresholds that are displayed in this plot, while at the same time we have very high efficiency above 98% for non-irradiated, of course, and also for very highly radiated chips. This is almost 2 10 to the 13, which is 10 times the expected lifetime for the inner tracking system, but we will see that this is not enough for other applications. And just to give you an idea, usually sensors that are tested and designed for high luminosity LHC, they are 10 to the 16. So they are almost 3 orders of magnitude more irradiated than this. Now, another application that is not present, but it's the next future, is focal. Indeed, focal, it's a calorimeter always in the LHC experiment that is foreseen for the next upgrade, and it's forward, and it has an electromagnetic calorimeter and an hadronic calorimeter. Now, for this talk, we forget about the focal age because it's not that we don't use monolithic there, but we focused on the electromagnetic part. And in particular, the electromagnetic calorimeter is a sampling calorimeter with 20 layers of tungsten. And after 18 of those 20 tungsten layers, there is what we call a low granularity layer. And these layers are with normal silicon detector hybrid, so they are silicon sensor wire bonded to a readout chip. But what we care in this seminar is the high granularity layers, because those are indeed made using alpides, the same alpides that we just saw. And the idea is that if we want to discriminate a single photon with two photons, or if we want to detect the isolated photon, we have to be able to see two photons that are very close to each other. And those are, this is not a simulation, this is actually from the test beam, where we see two photons that are very close to each other, actually two different layers, because we have the 5 layers that is early enough, so we start having a shower, but the shower is not too big, and then layer 10, where we see that the shower is a little bit bigger, but still we can discriminate the center of those two. Now, with respect to the ITS, of course, there are other problems. For example, material budget is not an issue since we have 3.5 millimeter of tungsten absorber just in front of the alpide. However, occupancy and acceptance are a problem. And also the fact that we want to read it out from outside the detector. And so our strings, we call them, while in the ITS jargon they are called staves, they are longer, and indeed we use 15 chips per string. And you can see here that we have 3 layers, 3 of those strings that are glued on top of an aluminum carrier, and this is the same but flipped, in a way that where there is sensor and then wires, then sensor, then wires, sensor and wires. When you flip it, the sensors are going to overlap where there are the connecting wires on the other side, and the wires are going to be overlapping with the sensor. In this way, you have full acceptance. And in particular, you can see it here, how we take the chips that I showed you many pictures so far, and then we go to a flex PCB that is not actually taking care of the readout, but is just rewiring everything and providing power. And some interesting thing is that we don't use wire bonding for this, but we use this technology that is called SPTAP. That is, I mean, it has pros and cons, but this is also one thing that we can do just because we don't have a very high density of the wire bondings, only because we are using a monolithic chip. So we can have a 27 times 29 micron pixel, and we can read it out using 65 micron of wire, which is of course larger than a single pixel, but we don't care because every single pixel is read out by the front end, by the readout electronics that is on board, and then we only have high-level data lines that are connected to the flex and so on. Okay, so now this is the present or the very next future. Now let's move on to the future, which is this that we call MOS. So first of all, what is the limitation that we want to address? Now this is the material budget of the ITS-2, and you can see that this is in fraction of radiation length, and there are peaks. So the first thing that you notice immediately is that it's not uniform. And the second thing that is actually very evident is that the silicon is just a little bit of it. It's 1/7 of the total material that is in front of the beam. So if we remove the water cooling, the blue, we are already improving the situation quite a bit. And we can remove the water cooling if we use air cooling. But of course, we can use air cooling only if the power is below 20 milliwatts per centimeter square, which means that we have to find a way to reduce the power of those sensors. Then we can also remove the circuit board that is reading the data. Like I showed you before, there are some wires. There is a flex PCB that is not really reading out the chip, but is providing the power and the readout connections for those chips that then can be read out from the side. You need those unless you embed them in the silicon. And so this is a possibility. And also, if you make it thin enough, and you don't need the readout, the circuit board, and you don't need the water cooling, you can make it thin enough that is flexible. And in the moment the silicon is flexible, you can bend it, and then in the moment is cylindrical, you don't even need anymore the structure. So you don't need anything in the way. Yes, you still need a little bit. Here you see those black things are carbon foam, but this is very light, and it's just a little bit adding the some material. Now you can see how this is mind-blowing, how you can improve just changing the sensor. And of course, this is impossible if you're not using monolithic technology. However, there is a problem. Now, the problem is that when they manufacture silicon chips in general, silicon everything like microcontroller, GPUs, silicon sensor, everything, the masking is not for the full wafer. So you have the wafer, and then you have this wafer is exposed to the actual pattern that is creating the chip one bit at a time. And this piece, which is called reticle, it's a lot smaller than the wafer itself. So the idea is that what we can do is that we can design a reticle, which is like the full monolithic chip and so on, but then we split it and we separate it in parts that then we can reassemble in a way that every reticle is exposed once, one bit at a time, but they can be one next to the other. And this is why it's called stitching, because those are very high resolution inside the reticle, but lower resolution at the edges. And so at the edges, you can stitch with basically wires inside the silicon. Now, with the real application of the MOS, which is now, it's obvious why it's called MOS, because it's a mosaic, because it looks like a mosaic. We can see that we have the central part where there is the pixel matrix, so the sensitive part, and then there are the control parts that can be stitched, and we can have a very long sensor with a control part only at the two sides. Now, once again, we are not really inventing something that we are only using. There are also some, in this case, it's a CPU manufacturer, which is also using wafer scale, and their application is for AI. Now you can see here that this is the Moore law. The number of transistors over the years is nicely going with an exponential law. This is logarithmic scale, of course, but there is another line, and like changing this is thanks to the fact that instead of waiting for the reticles to be wider, they use a stitched sensor. And you can see here, this is an actual wafer. You can see the stitching. You can see the size of the reticle and the stitching on the other side. And you can see how this very expensive per chip, but very cheap for the full production, you have overall a considerable advantage with respect to the normal technology. Of course, this is very elite, but also the MOS and the monolithic sensor are very elite. And so the cost is never going to be as low as a laptop CPU, but this is just a matter of producing thousands of them instead of millions of them. Okay, so seeing a little bit more in details what is happening in the MOS, This current prototype has two different matrices, and this is not going to be the case for the final one, but of course this is a prototype, so the designer wanted to test which one is better, and one has larger pixels, and the other is more efficient. So one is with so you have higher resolution, but of course, since the electronic is per pixel, you have more electronics, and so you have higher power consumption. Still, we are very far from the 20 milliwatts per centimeter square that is the limit, which I remind you is due to the fact that we don't want to use water cooling, but we want to use air cooling. Now, another difference between the prototype and what is actually happening, what is actually going to happen in the final one, is that we also have some control electronics on the side of the chip. And this is what we are using right now to test it, because even providing the power, we want to be sure that all of them are receiving the same power. So from the side, we can actually provide power or check that the voltages are correct. And the same goes for the control line and for the data line. We can use easier, faster lines from the side. And in the moment we finish the debug, we can move to what is going to be used in the final version, which is power, readout, and control, everything from the side. Okay, so this is the theory. Now let's see the practice. What you see here is a picture of the test beam that was done like a month ago. And here you see the beam. The beam line is passing here. This is in the east area at CERN. And what you see here are two boxes. Well, what you don't see is what's inside the box, because inside here they were testing, the ITS3 team was testing the baby MOS, which means a MOS with only one reticle. And now, actually, right now, they are preparing the test beam with a full MOS system, which is starting in next week. And here in the back, we have something similar but parallel. And this is the setup, which you also have monolithic, but those they are the alpides, because as I mentioned before, the radiation hardness of the alpide is fairly good, up to 2 times 10 to the 13, but we wanted to test for focal 10 to the 14. And so basically, I cannot show you the plot because it's still under approval, but well, and you know how it's working with the collaborations. But I can tell you that we managed to have at 10 to the 14, 98% efficiency applying the back bias. And so this means that the monolithic technology is actually very good, also 10 to the 14, which once again, it's 2 orders of magnitude less than what CMS and Atlas is testing for high luminosity LHC, but it's plenty for many applications, including the ILIS tracker and focal. Now, regarding the tests for the baby MOS, also, I cannot really show you much, but the efficiency of the non-irradiated chip is very high. They work fairly well, and I mean, of course, it's the first prototype, so there are a lot of things that we still have to learn, but they worked fine, and the irradiated ones, they are behaving consistently with what is happening with the alpide. Now, how are we working at the design of those new pixels? One of the things that we have to take into account is, for example, what happens when we are exposed to radiation. We already saw that the chips are resisting to irradiation over time, but we also need to see if when the alpide or the MOS is on, is actually working, the radiation is not damaging it. And in particular, what is happening is that when you have, this is inside the silicon, you can have some charges that are generated by the particle crossing, of course, because this is what you use to detect it. But if this is happening where you don't want it, this can create a charge funnel. So basically, it is a short circuit. Now, if this funnel is between power and ground of the sensor, you have something that we call single event latch-up. And latch-up is basically a short circuit that you have to, it's self-sustaining. So it's when the particle is gone, you still have the short circuit. And if you don't turn off the sensor immediately, you are going to burn the sensor. Another effect is a little bit more intuitive, is simply that this charge funnel is not between the power and ground, but is between the two sides of a transistor. And so it's basically flipping one flip-flop. If you have in your memory, you have at 0, it becomes a 1. If you have a 1, it becomes at 0. And this is called single event upset. Now, to fix this, you don't have to power cycle, but still, it's quite annoying that you have at 0 that becomes a 1. So to test for those effects, we designed chiplets that are exactly the same technology as the one that is used for the MOS, but they are dummy. They are just a memory. And this is what we call the SAU1, which is basically shift register. So just flip-flops one after the other, or a memory chip, which is SAU2. And you can see those are very small and very limited. I mean, they're just memories, but they are very useful because thanks to this, you see here the different lines, and here are the two sides, because those are the technologies that the designer are evaluating, which one is better, which one is more robust, which one is safer, which one we can afford, which one can work, which one cannot work. And so testing those chips is fundamental to assess what is the technology that is going to be used in the final version of the MOS. Now, what we did was actually to take this chip. Kansas didn't design the chip. It was designed the University of Bari, but we took it, we bonded it on a board, and then this board was controlled by a microcontroller, and everything was designed by Kansas. And then we used this to do two different tests. One was done in Louvain-la-Neuve. You can see here a vacuum vessel that is in front of a cyclotron, and we can decide which ions to shoot at the target. And the target is our poor SAU1 or SAU2 chip. And in this case, this is the cocktail that we decided to have. And you can see that we have the most important thing about this table is the LET, which is the linear energy transfer, which is basically the amount of energy that is deposited inside the silicon by those particles. And you can actually see how, if we have a heavier ion, it's releasing more energy. Now, increasing the energy of those particles is not helping, because if you increase the energy, the particle is going to travel more inside the silicon. But this is something that we don't want, because we want the particle to stop inside the silicon and to release a lot of energy. So what we did was to detect this kind of events, which are what we called single event latch-up, which means that basically the current of the chip was monitored. And at some point, the current was skyrocketing, was becoming, like you see here, from basically 0 was going to 60 milliamp. And then after we were powering it off. So in this, what you see is that this is generated by the single event latch-up, and then the short circuit is self-sustaining, so the current stays up, and then we were turning it off. And what we did was to measure the cross-section of this kind of events for different particles, for different LEDs, and we saw that, for example, some technology like this one, it's fine, because we were not able to detect anything. And like with supersymmetry, the only thing we could do was to put an upper limit. But for other technologies, for other designs of the memory, we saw that actually we could see some latch-ups even below the threshold that we call the maximum let expected at LHC, which is 15 MeV per milligram per centimeter square. So this means that we told the designer, look, you can use this technology, but it's better to avoid this other technology because it's more weak and is susceptible to single event latch-ups. Now, in a similar way, what we did was to measure the single event upset The problem is that we cannot use the same accelerator. We cannot use the same software. We're using the same hardware. You can see the boards here, but we had to go to another facility because what we need here is a lot of particles that are releasing a little bit of energy per particle. And so here you see the boards exposed to the proton beam, and you can see the cross section, and you can actually see how the amount of errors that we were seeing is proportional to the flux. So where are we going? There are other technologies that we can use instead of the tower jets that we saw with the Alpide. Now, one very promising technology is the HV CMOS. Now, basically, CMOS is the standard for the silicon technology. Everything in silicon is CMOS, but there are some ways to have high voltage CMOS. Basically, if you want to switch some high voltage source, or if you want to control simply, I don't know, the lights of your bedroom using a CMOS, this is the technology that you want to use. And this is the technology that Foundries developed for this task, because as you can imagine, there are a lot of clients for these kind of things. Now, we don't want, in this particular case, to turn on and off the lights of the bedroom, but what we want to do is to apply high voltage to the substrate. And so we need some silicon that is capable of sustaining this high voltage in a way that we can have a very high electric field between the two sides of the sensor. And so we can have a depletion layer that is very wide. And we can compensate for the problems that we had with Alpide, that most of the silicon, the charges were only drifting. Sorry, they were only diffusing and not drifting. In this case, since we have a very high electric field, they drift all the time. And so the collection time is a lot faster. And moreover, this is a commercial technology. So there are many foundries that can do that. Now, this is not only an idea. This is actually an idea that it's around since a few years now. And one prototype that is very recent is this 65 x 64 x 64 pixel matrix, and the pitch is bigger than the Alpide, so it's 62 micrometer instead of 29 x 27. But this is an advantage for us in focal, for example, because anyway we don't need that high resolution, and it is an advantage because you have, first of all, lower power consumption, and second, you have you have more space per pixel, and so you can have a smarter electronics. In this case, for example, you can have a threshold that is not global for the full chip, but that is per pixel, which is actually a very nice feature because you might have one region that is more noisy than the rest of the sensor. Another very interesting concept that is out there is that instead of using silicon wafer, we can use silicon germanium front end, which is faster and quite a bit more radiation hard. And the idea is that you can take advantage of those characteristics using a silicon germanium front end on top of a silicon detector. And once again, this is on the same piece of silicon. So basically you have a piece of silicon, and then you grow on top of it the silicon germanium part that you can dope, and you can have your readout electronics. Now, I'm showing you the results from a test beam, and like most of the slides, all the references are here. And what you can see is that in the prototype, they have very high efficiency, and also they have a time precision that is considerably higher than all the other alternatives. We saw before that for the Alpide, we had a time precision that is of the order of microseconds. Here we are talking about better than 20 picoseconds. So this is considered to be 4D tracking, so spatial tracking and time tracking at the same time in a monolithic sensor with very low power consumption, which is 2.7 watts per centimeter square. Now, of course, this is not comparable with the 10 milliwatts per centimeter square of the MOS, But there are two different technologies that are trying to solve two different problems. And this is also trying to solve, this is radiation R 10 to the 16, for example. But I didn't find any publication about that. But the rumor is that they are very radiation hard. Okay, so now let's see how do we want to apply those. First of all, we start with the LHC, path phase 2 upgrade, and LHCb in particular. Now the Sci-Fi tracker is a scintillating fiber tracker that is here. So it's not the vertex. The vertex is already silicon, but for phase 2, LHCb wants to replace it with the Mighty tracker, which is basically an hybrid in which you have the scintillating fibers like now for the low occupancy region. And this makes sense because scintillating fibers are relatively cheap. And then you have the central part that is the occupancy region with the HV maps, the ones that I just showed you. And of course, they have some requirements. But the idea is that you can see here the ghost rates. So basically, a pile up. It's going to go a lot better if we use the monolithics instead of the Sci-Fi. Now the idea is, can you use hybrid technology? Yes, it's just a matter of cost. If you use a high voltage maps or high voltage CMOS technology, you can produce you can produce wafers at the cost of a fraction of the cost with respect to hybrids because they are monolithics. You don't have to spend money for the hybridization and so on. And also because this is a commercial technology. So like I said, foundries have many clients, so they develop this technology for other kinds of application where the numbers are a lot higher, and so the cost per chip gets lower and lower. Now another example, and now this is the example of the silicon germanium monolithic that I showed, is with the phaser. Now phaser is always at the LHC. Now there is already a phaser, but the monolithics are going to be used for the upgrade, and the phaser is in a cavern that is not the main 0.1 cavern, but it's separated by hundreds of meters of rock. And the idea is to measure neutrinos coming from the Atlas interaction point. And also in this case, the main background is the main goal is to discriminate two jets due to two photons that are very close to each other. So very similar to focal, but we are talking about different problems. Of course, the occupancy is a lot lower. In this case, they need a lot higher occupancy. They need higher time precision. The requirements are different. They don't have many constraints on the power consumption. And this is why they are using the silicon germanium monolithic chip. And not the ones that I showed you, but the one without the gain layer that will have a little bit more relaxed time resolution. Now, to go a little bit even further in the future, we have the electron-ion collider, and now all the collaboration are joined, and they want to the effort is to design the EPIC detector, and the tracker is going to be very, very much inspired to the ITS-3 tracker. And in particular, we have, this is the inner region. There is the inner barrel, which is going to be we'll see now, but it's really the ITS-3 tracker. And then you have the vertex tracker, which are, they don't need the same low material budget, but they need they have a lot of surface. And also here you can see how there is the part, the outer part that is a gas detector, this MPGD, it means probably micromegas. And then there is also a time of flight, which is going to use ACL GADS, which is that there is going to be a lot less spatial resolution, but very high time resolution. Now, in more details, the central part is going to be, like I mentioned, very inspired to the ITS-3. Indeed, is going to use the ITS-3 MOS stitched sensor. and is going to use the same cylindrical pattern that the sensors are going to be bent. In this way, they reach a very, very, very low material budget. But at the same time, the same technology of ITS3, and this is different from Helix because Helix is using the ITS, the MOS only for the inner part. They also want to use the MOS for the large areas, not to take advantage of the material budget, but to take advantage of the fact that in the moment this technology is approved and it's working, is well tested, the cost is going to be very low because with one wafer you have one sensor and you just cut it and you put some wires and you have 12 inches of sensors already covered. Okay, so I mean, this was a very fast and very summarized overview of all the technologies. And I think we still have, well, I'm 1 minute late, but I guess that it depends on Daniel, but I guess we have some time for comments, and this is everything I wanted to say, but we have time for comments and questions.